exponential growth. And to remind you of what exponential growth was, we did, when we first talked about it, we talked about rabbits. Yeah, and we said, so exponential growth is when you grow by a constant multiple as opposed to a constant amount. So linear was like this, y equals b plus mx. And you grow by a constant amount. That was when we added 1,000 rabbits per year, every year. Just grow by a certain number of things. And that is the slope, right? That's the slope, how much you grow by. But then for exponential, it has a lot in common with linear. We said it's a0 times a to the x. And in this case, you grow by multiplying by the same thing every year or whatever the unit of time is. So in this case, a0 was the initial amount or y-intercept, and a is the constant multiplier. So for the rabbits, we had year, number of rabbits, linear, and number of rabbits, exponential. So we started with 1,000 rabbits in both cases. In year 0, we had 1,000 rabbits. And then for linear, you grow by 1,000 rabbits per year. So we have 2,000, 3,000, 4,000, 5,000, right, etc. But with the exponential growth, we grew by doubling, by multiplying by 2. So we went from 1,000 to 2,000, and then we went 4,000, 8,000, 16,000. So what marks exponential growth is this times something, right? To get from any number to the next, multiplying by the same amount. And what marks linear growth is the plus something. So my equations for these two things, after n years, I would have 1,000 plus 1,000 n, because I started with 1,000 and then I add 1,000 every year for n years. That's my linear equation. My exponential equation would be 1,000, because that's how much I started with. And then I'm going to double it over and over and over again. And multiplying by 2 over and over again, we represent by raising to the nth. Right? That just means repeated multiplication. So we have 1,000 times 2 to the n would be our exponential equation. So one classic example of exponential growth, aside from populations, is money. And when you invest money, it grows exponentially. It doesn't double, unfortunately, but right. So compound interest is a form of exponential growth, and it differs from simple interest. So in simple interest, assume you invest $5,000. If you're getting paid simple interest every year, you get paid, let's say, 5% of just the principal. So 5% of $5,000 is $250, right? So if you invested $5,000 using simple interest, you'd make $250 every year. Every year, you just add $250 to your bank account. But if you invest your $5,000 using compound interest, then you get to make interest on the interest. So if you have $5,000 and you invested at the end of 1 year, you make $250. But now you have $5,250, and you're going to make 5% of that, right? So you get to make interest on the interest that you made. So that's called compound interest. which differs from simple interest where you only make interest on the principal. So today we're going to talk about compound interest because it is a classic example of exponential growth. So suppose we invest $100, that's called the principal, your initial investment, in a bank account that pays 10% interest per year. So to compute the amount of money we have at the end of 1 year, we have to know how often the interest is credited to the account. In other words, how often is it compounded? So if we invest $100 in a bank account that pays 10% per year, at the end of 1 year, we would have $110, right? We would say, multiply your $100 by 1.1, because you keep 100% of it, that's where the 1 comes from, and you add 10% more, that's the 0.1. So you just multiply your $100 times 1.1, and you get $110. But suppose that the interest is compounded twice a year. So that means instead of applying an annual rate of 10%, it's going to be divided by 2 and applied twice. So we're going to get 5% every 6 months instead of 10% every 12 months. So at the end of the first 6 months, we're going to earn 5% of our interest. So we have our $100. We multiply by 1.05, the 1 because you keep 100% of what you have in there, and the 0.05 to add an additional 5%, and you get $105. So at the end of the 6 months, we have $105 in there. And then at the end of the year, we get another 5%, because they told us that we're earning 10% annually. So they have to give us the other 5%. So we take 5% and add that on to $105 instead of just $100. So we're really going to be multiplying by 1.05 twice. Once here, right? And then again at the end of 12 months. Once after 6 months and once after 12 months. And that actually comes out to $110.25. So how much more did we earn by crediting interest to the account twice rather than once? 25 cents. So make a little bit more money by crediting interest to your account more often. So what makes this exponential is that you're multiplying by the same number over and over again. Definition of exponential. So let's say we compound 4 times a year. Twice a year was better than 1. Let's try 4. So I'm going to have my $100, and this time I'm going to compound quarterly. That means 4 times per year. So every 3-month period, we receive 1/4 of our 10% interest, which is 2.5%. So each quarter, $100 gets multiplied by 1.025. 1 for 100%, keep 100% of what you've got, 0.025 to give you an additional 2.5%. And we do that 4 times to make a total of 10%. So after the end of the first quarter, we're going to earn interest on our interest, and after 1 year, we've received the interest 4 times. So we're going to multiply $100 times 1.025 4 times. Credit the interest to our account 4 times, 2.5% each time for a total of 10%. And let's pull up a calculator and see what that comes out to. Okay, 100 times 1.025 to the 4th, and I get $110.38. So by compounding 4 times per year, I get $110.38. A little bit more than if I compounded twice per year, which was $110.25. So let's say we were compounding monthly as opposed to 4 times per year. So how many months are there? 12. So I have to take my 10%, right, and divide it into 12 equal installments. So 10% divided by 12 is 0.833%. Right? Which as a decimal, right, because that's already written as a percentage, so as a decimal would be 0.0833. Yes, thank you. One more zero, you got to move that 2 to the left, 0.00833. All right, so that is, I'm getting 0.833% every month, but I get to keep 100% also, so I'm going to take my initial $100, and what do I multiply it by every month to calculate my new balance? Great. 1 for 100%, 0.00833 for the percent increase. And I'm going to do that 12 times over the course of a year. So I'm going to multiply that by 12. I'm multiplying 1.00833 12 times, so I raise it to the 12th. Okay, so let's see what this comes out to. So I get $110.47. $110.47. 9 more cents than I would when I compounded quarterly. So if I want to generalize this to n times per year, right? I want to divide the year into smaller and smaller intervals. So I did twice, and I did 4 times, and I did 12 times. I could do it, say, weekly, 52 times, or daily, 365 times, or twice a day. So I want to come up with a formula for n times. I want to generalize this to n times. Okay. So first thing I have to do is take my percentage, my 10%, right? And I divided it by n, the number of times that you compound per year. Right? That's what I did back here. I did the 10% divided by 12 to figure out what percent I'm making at each compounding. And then I had to change it to a decimal. So I have to do this, and then I have to multiply by 0.01, right? Move the decimal 2 to the left. So if I simplify this, I'm going to get 0.1 divided by n. So this is my interest rate that I make at each compounding. This is like the 0.00833. What did you do to that 0.00833? Back here. Yep, but first you added 1 to it, right? Because you get to keep 100%. And then we're going to raise it to the nth power. So I'm going to do my initial investment, $100, and then I do 1 plus the percentage I'm making at each compounding, and I do that n times per year. So this is how much money I would have in my bank account after n compoundings. I can just plug in an n, and I'll figure out how much money I have. So I did this, right, for 1, 2, 4, and 12, and this is the general formula. We just calculated. So, but what if I want to leave it in there for more than 1 year, and not just 1 year, but I want to have it in there for more than 1 year? Let's just say a whole year for now. Yeah, if it was going to be 2 years, I would say, well, I'm going to take my $100 and it's going to get compounded like that, right? But then I'm going to do that for 2 years. So n times a year for 2 years, so I'd put 2n here, because you just do it twice as many times. So instead of a 2, I'm going to put a t there. So that's what you do if you want to do it for t years as opposed to 1 year. If it was 1 year, you'd replace that t with a 1 and you'd get our formula for 1 year. So what I want to do is generalize this formula for any principal and any interest rate. So that's what I did here. This is the formula for interest compounding n times per year. You do your principal, you multiply it by some constant multiplier, which is 1 plus r over n, and then n times t is the number of times you apply interest to your account. So r is your interest rate as a decimal. P is your principal, n is the number of times you're compounding, and t is the number of years. So before we move on to continuous compounding, which is something a little different, I'm going to give you one more example. So I want you to calculate the amount in an account that starts with $500 and makes 6% interest compounded weekly for 3 years. Okay, so we have our formula. The amount in the account is equal to principal times 1 plus r over n to the nt. So what is my principal? What do I replace P with? $500. And R is what? 0.06. Yep, it's the percent interest rate, but written as a decimal. We divide that by n, the number of compoundings per year, which is 52 for 52 weeks in a year. And then we do 52 times 3. Then you just have to be careful with the order of operations when you're putting this in your calculator. So do what's in parentheses first. So I'm going to do 0.06 divided by 52. So within the parentheses, I'm doing the division first, right? Hit enter, and then I add 1 to that. And then the next thing I would do is the exponent, right? Because exponents come before multiplication. So I'm going to raise that to the, whatever the 52 times 3 is, 156. And then I multiply that times the 500. The multiplication is the last thing. So we get $598.54. Why did I round it down? When traditional rounding would have me round that up to 55 cents. Because it's money? Why does that dictate to round it down? Yeah, banks are never going to give you more. Yeah, they'll round it down. Yeah. Anybody seen Office Space? Yes. They have that scam where they take the parts of pennies. Yeah. Okay, so we okay with this? How to calculate this? All right. So we're going to move on to continuous compounding. So go back to our example with our $100 invested at 10% interest n times per year. What happens as we let the number of compoundings go to infinity, as we do more and more compoundings per year? Is it just going to, are we going to keep making more money? So when we compounded once per year, we made 25 cents. And we did twice per year, we got an extra 38 cents. So when I increased from twice, that gave me 25 to 38, 13 cents, right? An extra 13 cents. And then I went to monthly and I got an extra 9 cents. So you can check these later at home. I did them once a day, once an hour, and once a minute, and once a second. I calculated the amount in the bank if I compounded every single second. And it would be $110.51. So the surprising result is that your bank account does not grow arbitrarily large with the more compoundings. It has sort of this limit, this amount that it can't go above. So it keeps getting bigger by the smallest amount, but it's getting bigger sort of like this. It goes like that. So it flattens out and it's approaching this line and it's getting closer and closer and closer and closer, but it'll never pass it. So there's a limiting value to the number of times you compound. So if I look at this table of values here, I'm calculating something called the limit. I'm looking at 1 plus 1 over n to the n. So this would be what would happen if my interest rate was 100%, right? My interest rate was 100%. That would be my r, a 1. So if I have 1 plus 100% divided by n compoundings per year, and compound n times, when I let the n go to infinity, what does it look like the value of this expression is approaching? So I'm plugging in really big values of n, and I'm getting like 2.7 something. This number is approaching a really famous number called E. It's called E after the mathematician Leonard Euler, spelled E-U-L-E-R. So it's named after him. And this is a really famous limit. Okay, it's the limiting value is an important number. And it's 2.71828, et cetera, et cetera, et cetera. It's kind of like pi, right? It's an irrational number. So you cannot write it as a fraction of two whole numbers. That decimal goes on forever with no patterns, no repetitions. Just keeps going and going. So the natural exponential function is e to the x. So now that we have this important number e that shows up in one of the most classic examples of exponential growth, of compounding interest, we're going to look at what the function e to the x must look like. So e to the x is the pink line here between the two blue ones, 2 to the x and 3 to the x. Why does it make sense that it lies between 2 to the x and 3 to the x? Yeah, because e is bigger than 2 and less than 3. So it's going to lie between the graphs of 2 to the x and 3 to the x. Oops. And it's closer to 3 than it is to 2. So it's closer to the graph of 3 to the x than it is to 2 to the x. All right, so I'm going to go back to my compound interest example. How do we fit in E? So we plugged larger and larger of values of n into this expression. And the only difference between this expression and the one that goes to E is that this is a 0.1 instead of a 1, right? So as n increases, the value of 100 times 1 plus 0.1 over n to the n approaches 100 e to the 0.1. So let's just check it on our calculator. 100 e to the 0.1 should come out approximately to what I got when I compounded the interest like every second. So 100. The E button on your graphing calculator is 3 up. It's in the second function. So e to the x here, you hit second, and then the e to the x button, and it automatically asks you what you want to raise it to, because it's so frequently used as the base that it automatically asks you for an exponent. So I put in 0.1, and enter, and I get this almost this number that I got when I compounded every second. So as n gets large, we think of the compounding occurring at every instant. We think of it as though we compounded our interest an infinite number of times per year. And we call this continuous compounding, continuously calculating the amount of money in your account. So our formula for compound interest is this. This is the one we already came up with for n times per year. But if the interest is compounded continuously, so you have to watch for this word continuously, that means that interest is being earned at every instant. This is our new formula. What happened? Oh no. So compounding continuously, watch for the word continuously. We have a new formula for that, PE to the RT. Principal times E, which is just that irrational number, 2.7, blah, 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 to the R, which is the interest rate as a decimal, times T. So take a minute, use the formula, find the amount of money you have after 10 years if you invest $1,000 at an interest rate of 4% compounded continuously. Okay, so here's our formula. A equals PE to the RT. What's the principal? $1,000. E is just a number. You can use the button on your calculator for it. And what's my interest rate as a decimal? 0.04. Yeah. And T would be 10 years. Okay, so now I just have to put this into my calculator. Careful to follow the order of operations. So I could do 1,000 times, I use this e to the x button, second e to the x, and it asks me what I want to raise it to. Well, 0.04 to the 10, I could do it in my head. I could say that's 0.4, 0.04 times 10. Or I could just type it in, and just because it's in parentheses, the calculator will do that first. It will multiply 0.04 times 10. Then it'll do the exponent, then it'll do the multiplication, because your calculator knows the order of operations. So enter, I get $1,491.82. That's just how much is in your account after 10 years. You'll have more if you leave it in longer. Or you could have more if you had a better interest rate, right? So that's a good question, actually. Exponential functions have no maximum, right? This one started at $1,000, and it's just going to keep going up like that. The longer you leave it in, the more money you have in the account. This is why they tell you to start putting money in your retirement account when you're young. The longer it's in there, the more it'll be worth later. Okay, so now here's a more interesting question. Same principal, same interest rate. How long till the investment doubles? Do a little trial and error. Think about it. See if you can figure out how long it will take to get $2,000. Just down to years, yeah. Okay, we have several things we can do to try to solve this. So how long will it take for it to double? So I want to know how long, so the question is how long, which means I'm probably going to be solving for t, time, until the investment doubles. So that's until the amount in the account is $2,000. So this is the equation we want to solve. We don't have an algebraic tool to solve this yet. Okay. Don't have an algebraic tool to solve it. So we're going to have to either do something numerically with trial and error or graphically. So we'll use the calculator for both of those. So we could just type in 1,000 times e to the 0.04 times stuff times e to the 0.04 times, I know 10 was too small because that only got me to 1490 something. So maybe I'll try 15 years. Still too small. Okay, so maybe now I'll try 20 years and I can use the little trick where I do second entry and I get everything that I just typed in. And now I can just change the 15 to a 20. And I go, oh, okay, that's too big. That's too many. So something between 15 and 20, maybe 17. Oh, that's pretty close. $27 off. So maybe I'll try 18. Too big. 17 and a half. Too big. Okay, so 17.3. Really close. Okay. 3.5. Okay. 17.35. Super close. Okay. Super close. So a little more than 17 years, we could say. So another thing we could do is do this trial and error by using the table function in our calculator rather than typing it in over and over. So if you go to y equals and we put 1,000 e to the 0.04, oops, 1,000 e to the 0.04 x, then what I did in the home screen is I just plugged in different values for x. I can have the calculator do that in my table. Just type in all different values for x. I could do 10, 15, 20, and narrow in on it by using the table and not having to do so much typing. So 17, too small, 17.3, a little small, 17.375, pretty close, a little big. So you can use the table. Last thing we could do is solve it graphically, which we learned how to do way back at the beginning of the semester. So I have y equals, I have the right side of my equation in y1, put the left side in y2. So one side in y1, the other side in y2. And then I want to see where they cross. So I have to pick a window that makes sense. X is representing time, so I'll go 0 to, I know, now that I've solved it, I know 17 is the answer, so maybe I'll go to like 25, just to make sure I can see the intersection point real well. And then I know I want them to cross at a y value of 2,000, because y equals 2,000 is just a horizontal line at a height of 2,000. So I just need to be able to see that, so maybe I'll go like 1,900 to 2,100 for y, just to make sure I can see my horizontal line. And we graph it. So this one that's increasing represents my bank account. It's growing, right? And this horizontal one represents a value of $2,000. So I find out where they cross by using the calculate menu, choose option 5, intersect, and you just hit enter, enter, enter. And we get 17.32868. Yep. You can, but we haven't learned logs yet. Yep. But logs or the algebraic way of solving this, which we'll do in the next couple classes. Yeah. So to be more exact, 17.328. Okay, so the last thing we're going to talk about today is half-life and radioactive decay. So the half-life of a substance is the time required for 1/2 of the current amount to decay, to go away. Okay, so this is my general form for half-life of a material. So M0 is your initial amount, and then you're going to multiply it by 1/2 over and over again. You're halving it. And the number of times you have it, H-A-L-V-E, the number of times you cut it in half, is you take the T, the amount of years that have passed, and you divide by the half-life, the number of years it takes to have. So if the half-life is 1,000 years and 6,000 years have passed, then you would say, well, that means that it got halved 6 times. So to get that 6, we took the time that has elapsed divided by the halving time, the half-life. Okay, so this is our general formula. Here's a classic example. Tritium, it has a half-life of about 12 years. It's used to catalyze the reaction in a nuclear weapon. Suppose a weapon contains 1 kilogram of tritium. How much is remaining after 50 years? So we'll write down the formula. M of T is equal to M0 times 1/2 to the T over H. Okay. So what's my M0? 1 kilogram. How much time has passed? 50 years, and my half-life is 12. So the amount I have left, I can just calculate by putting this in my calculator. I do have to be careful with the order of operations. I'm going to do 1/2 to the 50 over 12. Put parentheses over the 50 over 12 because you want it to calculate that before doing the exponent. And then we just multiply by 1, which isn't going to change anything. So we get 0.05568 kilograms. Which would be 55.68 grams, right? 1,000 grams in a kilogram. Okay, so I'm going to have you work on this one. We have the burial cloth of an Egyptian mummy. It's estimated to contain 59% of the carbon-14 it originally contained. So this is called carbon dating, using carbon-14 to figure out how old something is. We want to know how long ago the mummy was buried. So that is the thing you're going to be solving for is T, because they're asking how long ago. So you're going to have to solve it graphically like we did with the money one. Okay, so if we have 59% now, how much did we start with? 100%. Okay, so I'm going to put the amount we have now is going to be 59, and M0, the amount we started with, is 100%. And time is what I'm trying to solve for. H is 5,730 years. That's the half-life. So I want to solve for T. I'm going to have to do it graphically or by trial and error. So pull up my graphing calculator, go to y equals, clear what's there. Put one side of your equation in y1, and the other side in y2. And I don't have a button for t, so I use x in the graphing calculator as my variable. Now I have to choose a window. The problem gave me a window to work with, but let's just try to think it through rather than using what they told us. Okay, so t is time. How old do you think an Egyptian burial cloth might be? 100 years old? Older? Thousands of years old? 6,000. Okay, let's, 0 would be like the oldest, the youngest it could be, right? As if it was new. That's impossible. Then maybe we'll put 10,000 years, right? That was a long time ago. And then for Y, which represents percent of the cloth, percent of C14 left in the cloth, the lowest would be 0 and the highest would be 100, right? Because Y is representing percentage left of the C14. So we graph it, and I want to know where these two cross. The one that's going down, the line that's decreasing, is representing the amount of C14 in the burial cloth, just changing over time. And the horizontal line represents 59%. So I want to know where they intersect. So I could do second, calculate, intersect, enter, enter, enter. And I get 4,361.7 years old. So T is approximately 4,361.75. So for now in your homework, when you're asked to solve an exponential function for t, you solve it graphically. And then after a couple more classes, you'll be able to solve it algebraically. Oh, I wanted to show you this little applet, growth. And we can make the birth rate various things like, say 2. The population doubles every generation. So you can run it, and it just shows the population doubling. Okay, so yes, it's on your. So imagine that this is your bank account. This is $1 and not a fish, right? So if I make the birth rate double, you have a lot of dollars really fast. But even if I do less than doubling, if I do like 1.1, that's a 10% interest rate, and run it, you can see how many fish we have. So it's growing pretty meagerly at first, and then it's going to take off. Now we have a pretty decent number of fish. Yes, this would be the year. Yep. Or however often you're getting your 10% interest. This is why they say it takes money to make money. Right?